Hello, I'm Seema and welcome to part 35 of the chapter Equilibrium. In this video, I'm going to tell you the relationship between Ka and Kb, where Ka and Kb are the ionization constants. Ka is ionization constant for acids and Kb is the ionization constant for bases. What is an acid-base conjugate pair? A conjugate acid-base pair is one which only differs by a proton. That is, any substance that is an acid, its conjugate base only differs from it in being one proton less than the acid. And why? Because an acid is something that releases a proton. So when it releases a proton, what is left is something, the same species minus one proton. So what would the conjugate base be? A conjugate base is nothing but one proton less than the conjugate acid, right? So here is an example of a conjugate acid-base pair, that is ammonium and ammonia. They are a conjugate acid base. And if you really look, ammonium ion has one proton more than ammonia. So you can guess from this which one would act as an acid. According to the Arrhenius definition, anything that is a proton donor would act as an acid. And ammonium ion would lose the proton to form ammonia, therefore ammonium ion is the acid. And according to the Bronsted definition, anything that accepts a proton acts as a base. So if ammonia acts as a base, it accepts that proton and results in the formation of ammonium ion. So taking these two opposite reactions, that is, or rather the reaction of the conjugate acid base separately, let us study these reactions and then find out the relationship between these two. Ammonium ion combines with water, or in the presence of water. It dissociates, it gives a proton and results in the formation of hydronium ion and ammonia. So the conjugate base that is formed is ammonia. This is an acid, and if you want to find out the value of Ka, that is the ionization constant for this acid, you will write down the concentrations of the products divided by the concentration of the reactant, and we ignore the concentration of water because water is a liquid. So the ionization constant would be, or Ka would be H3O positive into NH3 divided by NH4 positive, which is the reactant, and this is equal to 5.6 into 10 to the power minus 10. At the same temperature, if you carry out this reaction of ammonia and you dissolve ammonia in water, ammonia acts as a base. And when it acts as a base, it means it accepts a proton from the water. And when it accepts a proton from the water, it results in the formation of ammonium ion and OH negative. Now, if you find out the equilibrium constant for this reaction, it would be Kb, because here NH3 is acting as a base. So we call it the dissociation constant or the ionization constant of the base. So Kb would be equal to the concentration of products divided by the concentration of reactant, ignoring the concentration of water as we did because it's a liquid. And the value at the same temperature is found out to be 1.8 into 10 to the power minus 5. Now, we have now found out the values of both Ka and Kb for this conjugate acid-base pair, that is ammonium ion and ammonia. What is interesting, we can draw a relationship between these two. If you take these two reactions which I have underlined with green, that is where ammonium is acting as an acid and ammonia is acting as a base. Let us find out the sum of these two reactions. Okay, add up these two reactions. If you add up these two reactions, you will get a net reaction. So let us add it up. Ammonium here is in the reactant and ammonium here is in the product, so it will get cancelled out, right? The hydronium ion is present here and the hydronium ion is not here, so it remains. Water, of course, remains because it's in both the reactions. Then you have ammonia in this reaction and ammonia in this reaction, which get cancelled out. So what are you left with? You're left with water in this reaction, you're left with water which couldn't get cancelled out, you're left with hydronium ion and you're left with the OH negative ion. Do you see? So if you write down the sum of these two reactions, what will you get? You'll get 2H2O gives you H3O positive plus OH negative. And what is this? This is actually the reaction for this is actually the secondary reaction for both of these reactions, where water acts, one molecule of water acts as an acid, one molecule of water acts as a base, and they react with each other, resulting in the formation of hydronium ion and OH negative. And if you remember, in the previous videos, we found out the ionic product of water. So if you find out the equilibrium constant for this reaction, we know would be H3O positive into OH negative divided by nothing, because it will be 1, because water is a liquid and therefore its value would be 1. It is whole, the concentration. So you'll get only the ionic product of water, that is the product of the ions in water, which is H3O positive and OH negative, and this is equal to 1 into 10 to the power minus 14. So what did we notice? We noticed that when we summed up or added up these two net reactions, we got the net reaction that we got was actually of this, which led us to the ionic product of water. So if we take these values, let us see what would be their relation. If you find the product of Ka and Kb, Ka into Kb can be represented by the net reaction. Ka into Kb would be what? Ka is H3O positive into NH3 upon NH4 positive. And what is Kb? Kb is NH4 positive into OH negative upon NH3. Again, if you see, you will cancel out NH3 here and NH3 goes here, NH4 positive goes here and NH4 positive goes here, and what are you left with? You are left with the ionic product of water, which is 10 to the power 1 into 10 to the power minus 14. So just to verify this, when you multiply these two values of Ka and Kb, they should be equal to 1 into 10 to the power minus 14, and that is what we find them out to be. So what is the relationship between Ka and Kb? That when you have an acid-base conjugate pair or a conjugate acid-base pair, the product of their equilibrium or the dissociation constants is equal to the ionic product of water. This is the relationship between Ka and Kb. That when you find out their product, it is equal to the ionic product of water. Now, not limiting it just to the acid-base conjugate pairs, let us take some reactions which are consecutive reactions in many steps. So this can be extended, this concept can be extended, and you can generalize it. And how would you generalize it? When you generalize it, the statement that you could give from this knowledge is that the equilibrium constant for a net reaction obtained after adding two or more reactions equals the product of the equilibrium constants, the net reaction. The equilibrium constant for the net reaction is the product of the equilibrium constants of the individual reactions, is the product of the equilibrium constants for the individual reactions. So K net, if there are, let us say, 3, 4, 5 reactions, would be K net would be K1 into K2 into K3 into K4 into K5 and whatever number of reactions you have. So the net reaction would always be a sum total of all the reactions, and the equilibrium constant of the net reaction would be a product of the equilibrium constants of all of those. And for conjugate acid-base pair, which we've already done here, Ka into Kb is equal to Kw, where Kw is the ionic product of water. This particular relationship can also be obtained from the base dissociation constant, or the reaction for the base dissociation. For example, B is a base, and in water, an aqueous solution of the base in water, it results in the formation of BH positive. We know a base is something that accepts a proton. So it will be BH positive, and from water it accepts a proton, and what is left of the water molecule? OH negative. If you write down the Kb value for this, you would get BH positive into OH negative divided by B, and water is a liquid, therefore it's 1. Its value is 1 and we ignore it. So BH positive into OH negative upon B. Now if we divide this reaction on both sides, or rather multiply both sides by H positive, what will we get? Both sides means the numerator and the denominator. We are multiplying it by H positive. So you get BH positive into OH negative into H positive upon, you will get B into H positive. Or if you rearrange this, OH negative and H positive can be brought together, and BH positive would be divided then by B and H positive, right? What we have done in this step is just rearranged these. We just took the OH negative and H positive separately. We took the BH positive on that side and divided it on purpose. We brought all of these together. Why? Because B into H positive upon BH positive, when B gains a proton and it results in the formation of, when BH positive loses a proton, it results in the formation of B, the base, and H positive. This is the opposite reaction. So if you really look at this, if you take these to be the products and this to be the reactant, then this value actually becomes equal to Ka. What is Ka? If you had a reaction like VH positive, BH positive was dissociating in water to give you B plus H positive, that is H3O positive, so which can be written as H positive. So if you write down the equilibrium constant for this, you will get Ka for this acid BH positive, just like we had for ammonium ion. You would get B into H3O can be written as H positive upon BH positive, right? And isn't it what you see here? Only the numerator is in the denominator. Therefore, Ka would be in the denominator. So you get this value is Kw. This is the ionic product of water, right? This term is the ionic product of water, and this term is the inverse of Ka. So you get Kb is equal to Kw upon Ka. So in other words, what is Kw? Kw is Ka into Kb. Bring the Ka up here. It will be Ka into Kb would be equal to Kw. Also, if you had to find out the pKa values, extend the pH, the concept of pH to all of these, then pKa is whatever its value is, pKb whatever its value is. When the ionic product, when Ka into Kb is equal to Kw, which is 10 to the power minus 14, that is, the product is always 10 to the power minus 14, then their pKa and pKb values should also be equal to the pKw value of the ionic product of water, which should be, and this pKw value should be equal to 14, because the minus log of 10 to the power minus 14 is 14, right? So this was about the relationship between Ka and Kb. Let us now solve one solved example on this topic so as to finish it up. Give me a moment, let me write it down. Alright, so now this is question 7.23 of your NCERT textbook. It's a solved example, and by explaining this, I'm sure you'll be able to understand this relationship, and a little revision of the previous topics that we did too. It'll help you really solidify the topic better. The question reads, determine the degree of ionization and pH of a 0.05 molar solution of NH3, that is ammonia. Now what all are you to find out? You have to find out the degree of ionization, you have to find out the pH, okay? You have to determine the degree of ionization of what is given to you, 0.05 molar solution, that is concentration C is given to you, of ammonia solution. The ionization constant of ammonia is 1.77 into 10 to the power minus 5. Ionization ammonia is a base because it gains a proton and results in the formation of ammonium ion. Therefore, this ionization constant would be it would be Kb. So these are the things that are given to us. Also, you have to calculate the ionization constant of the conjugate acid. Ionization constant of conjugate acid means you have to find out Ka. Now, what all are we given? We are given C, which is C of ammonia, which is 0.05 m, and Kb is given to us, which is 1.77. Actually, in the question, they told you that you have to look into the table for this. And I just wrote down the value because the idea of making students look into the table is just to give you a little idea how scientists actually who are working on these, they do it. They do not have all values given to them, so they have to go to these reference tables, they have to find out the values from there, and then they proceed with their work. This is just a little a way to give you an idea or to give you a taste of what it is like when you're working as a scientist. But basically it is just a little one step more to refer to a table, otherwise the value is given to you. So KB is given to you, C is given to you, and what are you asked for? You've been asked for Ka, you've been asked for degree of dissociation is alpha, is asked for, the pH is asked for, and Ka is asked for, right? So these are the things that you need. So let me start writing the equation first. The equation would be, you have ammonia. Ammonia combines with, I'm not writing the states and all, combines with water, we already know what it is, to give you ammonium ion plus OH negative, right? The initial concentration C is 0.05, that is C is 0.05 for ammonia, and initial concentrations of ammonium and OH negative are 0. So the degree of dissociation you have to calculate, which means that C alpha would be the amount that reacted. So C alpha would be equal to 0.05 alpha. And what would be the amount minus C alpha? Would be the concentration of ammonia at equilibrium, right? And addition of C alpha would be 0.05 alpha plus 0.05 alpha. So at equilibrium, what would the concentrations be? It would be 0.05 minus 0.05 alpha, and this would be 0.05 alpha, and this is also 0.05 alpha. Right? So what is the first thing that is asked of us? You have to find out the degree of ionization. You have to find out the value of alpha. In order to find out the value of alpha, what do? You put these values in the value for the equilibrium constant. And equilibrium constant is given to us. So Kb is equal to, I'll write the value later. Kb is equal to the concentration of ammonia, NH4 positive into OH negative divided by NH3 concentration, right? And this is equal to, what is the concentration of ammonia? 0.05 alpha, and OH negative is also this, so this would be square of this, divided by the concentration of ammonia is 0.05 minus 0.05 alpha. Now let us simplify this. This would be let us take the 0.05 outside, 0.05 square alpha square, so alpha square upon 0.05 into 1 minus alpha. And you know the 0.05 and the square of this, so 0.05 is cancelled, so you're left with 0.05 alpha square upon 1 minus alpha. No, I'm doing it in just one step. I could have done it in two to explain this. So if you take the 0.05 common here, then you are left with 1 minus alpha, and the 0.05 and 0.05 cancel out. You're left with 0.05 alpha square upon 1 minus alpha. Now alpha, the degree of dissociation for a weak base is very, very little. In order to simplify our calculations, we'll assume that 1 whole is so much that just a very little amount that dissociated, the degree of dissociation in the denominator here really doesn't matter. It's almost approximately equal to 1. So in order to simplify, to make our calculations easier, and even otherwise practically, the alpha in comparison to 1 is very small, it is negligible. So let us neglect it. And now let us put the value of Kb. So this becomes 0.05 alpha square is equal to, upon 1, because alpha we can ignore, is equal to 1.77 into 10 to the power minus 5. Therefore, from this, if you have to find out the value of alpha, alpha square, in other words, would be 1.77 into 10 to the power minus 5 divided by 0.05, and alpha would be the square root of this value. So when you calculate this, the value comes out to be equal to, the value of alpha is 0.018. From this you can calculate the value of alpha to be equal to 0.018 So that is the first part of the question. 0.018 is the value of alpha that you calculate. So what's the next part of the question? What is the pH? How do you calculate the pH? We know that ionic product of water, Kw, is equal to H positive into OH negative. Kw we know is 10 to the power minus 14, and H positive we have to calculate, and OH negative we have already calculated here is 0.05 alpha. So into 0.05 into, and what is alpha? 0.018. So you can calculate the value of OH negative from here. And from that you can calculate H positive. So what would H positive be equal to? The concentration of hydrogen ion would be 10 to the power minus 14 divided by this value, which is 0.05 into 0.018. And when you calculate this, this comes out to be equal to the concentration of H positive ion comes out to be 1.06 into 10 to the power minus 11. 1.06 into 10 to the power minus 11, right? Moles per liter. So that is the concentration of hydrogen ion. From this, you can calculate the value of pH, right? So pH would be the negative log. pH would be equal to minus log of H positive concentration, which is equal to minus log of 1.06 into 10 to the power minus 11. And when you calculate this value, the pH comes out to be how much? 10.97. 10.97 is the pH. So you calculated pH also, it is 10.97. Now you're left with the third part of the question, that is to calculate Ka. We also know, according to this relationship between Ka and Kb, we have the value of Kb. We have the value of Kw. You have to find out the value of Ka. We know that Kw is equal to Ka into Kb, right? So Ka for what? For a conjugate acid-base pair. So what's the question? You have to calculate the ionization constant of the conjugate acid. So for a conjugate acid, Kw is equal to Ka into Kb. And therefore we already have Kb. So what would Ka be equal to? Ka would be equal to Kw upon Kb. And Kw is 1 into 10 to the power minus 14 divided by, what is Kb? Kb we have calculated. No, Kb is given to us. 1.77 into 10 to the power minus 5. And when you calculate this, this comes out to be how much? 5.64 into 10 to the power minus 10. It comes out to be 5.64 into 10 to the power minus 10. So that gives us the value of Ka. So do you see? Whatever you've learned in the past few videos, this question really kind of uses all of that information. So if in case you're finding it difficult to understand this question, I would encourage you to go back a few videos, watch all of them, and then come back and solve the problems, and keep solving the problems as and when they come. And by the time you come to this video and you do this problem, you'll find it really easy. So with that, I'll finish today's video. If you found it helpful, I would appreciate it if you gave it a thumbs up. Subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.